Today's lecture examines how city planning can respond to a changing climate. We will consider rising temperatures, intense rainfall, urban vegetation, building arrangement, land use controls, and public health planning. The central idea is that climate hazards interact with the physical form of a city and with the social conditions of its residents. A weather event does not produce the same outcome everywhere because streets, buildings, services, and population characteristics differ. Let us begin with temperature. Urban areas are often warmer than nearby rural surroundings, particularly during calm nights. This pattern is commonly known as the urban heat island effect. One cause is the replacement of vegetation and moist soil with roofs, roads, and paved surfaces. Dark materials absorb solar energy during the day, store part of it, and later release it as heat. Closely spaced buildings can also reduce the rate at which stored energy escapes toward the open sky. Vehicles, air conditioners, industry, and other activities add further warmth directly to the urban environment. The effect varies across a city rather than forming one uniform temperature zone. A district with mature trees and open ground may remain cooler than a nearby area dominated by wide roads and unshaded buildings. Removing trees reduces daytime shade for pedestrians, playgrounds, homes, and public transport stops. This can make walking uncomfortable and increase the amount of solar energy entering buildings through windows and walls. At night, however, a dense tree canopy may sometimes reduce outgoing radiation, so planners must consider local conditions rather than apply one rule everywhere. We can now turn to water. Warmer air can hold more moisture, and in some regions this contributes to heavier rainfall events even when annual rainfall changes little. A sudden storm can deliver water faster than a city was designed to carry it away. Heavy rainfall may exceed the capacity of underground drainage systems, causing water to collect on streets or enter buildings. Blocked inlets, undersized pipes, low-lying roads, and construction over natural channels can all worsen the outcome. River flooding and coastal flooding create additional risks, but they involve different pathways and may require different protective measures. Traditional engineering often attempts to move storm water away rapidly through pipes and channels. That remains necessary in many locations, yet planners increasingly combine it with surfaces and landscapes that slow, store, or absorb water. Permeable paving contains spaces through which rainfall can pass, increasing infiltration into the ground below. Rain gardens collect runoff in shallow planted areas, where soil and roots delay the flow and may filter some pollutants. Retention ponds hold water for longer periods, while detention basins are usually designed to empty after a storm. These terms sound similar, so the intended duration of storage is important. Green roofs can also hold part of a rainfall event before water reaches street-level pipes. Their performance depends on soil depth, plant type, previous rainfall, roof design, and maintenance. Vegetation provides more than water management. Leaves intercept sunlight, and trees cool surrounding air partly through transpiration. During this process, water moves through a plant and is released as vapor from small openings in its leaves. Energy is required for the change from liquid water to vapor, which produces a cooling effect. Trees can therefore reduce local temperatures, but they require adequate soil volume, water, suitable species, and long-term care. Planting a young tree does not provide the same immediate benefit as protecting a healthy mature one. Species selection also matters because future conditions may differ from the climate in which existing trees were established. A species that tolerates today's summer may struggle under more frequent drought or new pests. Urban green areas should not be treated as isolated decorative sites. Connected green corridors allow birds, insects, and other wildlife to move between larger habitat areas. Connections can follow rivers, railway edges, tree-lined streets, or linked parks. A narrow connection will not serve every species, and a route interrupted by major roads may still create barriers. Nevertheless, planning at network scale is usually more useful for biodiversity than counting parks alone. Building form and street layout create another set of climate effects. Very narrow streets between tall buildings may block wind at pedestrian level, although they can also provide protection from strong sun in some climates. Street orientation, building spacing, and differences in roof height can support natural ventilation between buildings. Improved air movement may remove accumulated warmth and some pollutants. Yet stronger wind is not always desirable, especially in cold seasons or around exposed towers. Designers therefore use local weather records and computer models to test several arrangements rather than simply maximize airflow. Buildings themselves can reduce risk through insulation, external shading, reflective materials, and efficient cooling systems. Mechanical air conditioning protects occupants during extreme temperatures, but it also consumes electricity and releases waste warmth outdoors. Passive measures can lower cooling demand, although they must be matched to humidity, sunlight, building use, and local construction practice. Planning also determines where development occurs. Land use zoning can restrict housing, hospitals, or essential infrastructure in locations exposed to floods, fire, erosion, or unstable slopes. Building codes perform a related but different function by setting standards for structures that are permitted to be built. A code might specify floor height, drainage connections, insulation, or resistance to wind. Zoning concerns the suitability of the location, while a building code concerns the performance of construction. Risk maps support these decisions, but a map is not permanent truth. It must be revised when rainfall data, sea level, land cover, drainage networks, or development patterns change. Climate planning also has a social dimension. Extreme temperature affects everyone, but some residents are more vulnerable because of age, illness, poor housing, outdoor work, isolation, or limited access to cooling. A citywide average can hide neighborhoods where exposure and poor health overlap. Heat action plans may establish warning thresholds, check on isolated residents, adjust school or work schedules, and extend the opening hours of cool public buildings. Communication must reach people in appropriate languages and through channels they actually use. Authorities should also avoid assuming that advice alone solves a problem when residents cannot afford electricity or travel to a cooling center. Finally, we need to distinguish mitigation from adaptation. Mitigation reduces the emissions that drive future climate change, for example through efficient transport, cleaner energy, and lower building demand. Adaptation means preparing for climate effects that can no longer be completely avoided. Flood storage, heat health plans, drought-tolerant planting, and revised construction standards are examples. Many actions support both goals. A shaded walking route can reduce heat exposure while making low-emission travel more attractive. However, conflicts are possible, and planners must evaluate costs, maintenance, access, and unintended effects. To conclude, climate-responsive planning connects physical design with environmental processes and social needs. Effective action requires evidence at neighborhood scale, coordination across services, and regular review as conditions change.
Today's lecture considers the effects of screen time on sleep, attention, physical comfort, and daily behavior. The phrase screen time covers many activities, including study, employment, video calls, games, social media, reading, and entertainment. These activities differ in purpose, content, duration, and social setting, so one total number cannot explain every outcome. We must also distinguish association from cause. People who use screens heavily may differ in sleep schedules, work demands, health, or family circumstances before the screen activity is measured. Good research therefore considers both direct mechanisms and activities that screen use may replace. Let us begin with sleep. Light is an important environmental signal for the human body clock. Exposure to bright light in the evening can shift biological timing later, particularly when the light reaches the eyes close to the usual sleep period. Evening light exposure can delay the normal rise of melatonin, a hormone associated with the beginning of the biological night. Shorter wavelengths, often described as blue-enriched light, can produce a strong response, but brightness, distance, duration, and timing also matter. It would be misleading to claim that one color alone determines whether a person sleeps well. Modern devices can reduce short wavelength output at night, yet a bright display may still affect timing, and the activity itself may keep a person awake. Content provides a second pathway. A calm electronic book and a competitive online game may involve similar displays, but create different levels of excitement. A third pathway is simple delay. A person continues watching, reading, or communicating beyond the intended bedtime. This loss of sleep opportunity can be more important than the light emitted by the device. Notifications create an additional problem when a device remains beside the bed. A sound, vibration, or illuminated screen may wake the user after sleep has begun. Even without an alert, expecting a message can encourage checking behavior. We can now consider attention during waking tasks. Digital tools support research, communication, and rapid information retrieval, but they can also present competing demands. Alerts and incoming messages create repeated interruptions during reading, writing, or problem solving. After each interruption, the user must remember the previous goal and reconstruct where attention had been directed. This recovery takes time even when replying to the message itself requires only a few seconds. Some people describe frequent switching as multitasking. However, when two tasks require conscious thought, the brain usually switches between them rather than processing both fully at once. Frequent task switching may reduce sustained concentration and increase errors, particularly during complex work. The effect depends on task difficulty, experience, motivation, and whether the interruption was chosen or unexpected. Background music may have little effect on a familiar routine, but interfere with learning difficult verbal material. We should therefore avoid treating every second screen or background sound as equivalent. Screen use also interacts with physical activity. A person can meet exercise recommendations and still spend long uninterrupted periods sitting. Long periods of recreational screen use can encourage sedentary behavior when they involve little movement and continue for many hours. The health concern is not that the display itself prevents exercise, but that inactive time accumulates and movement breaks disappear. Work and study screens create similar patterns when desks and schedules are poorly organized. Short movement breaks can interrupt sitting time without requiring a complete exercise session. Physical comfort is influenced by equipment arrangement. A laptop placed low on a table may require the user to bend the neck and round the shoulders. Poor device position can produce unsuitable posture, increasing strain in the neck, shoulders, back, or wrists. Raising the screen may improve neck position, but a separate keyboard may then be needed to keep the arms comfortable. There is no single perfect position that can be maintained indefinitely. Variation, support, appropriate equipment, and regular movement are all important. Eye discomfort is another common concern. Looking at a nearby display requires sustained focusing, especially when text is small or contrast is poor. People also tend to blink less often during concentrated close visual work. Reduced blinking allows the tear film to break up, contributing to eye dryness, burning, or a gritty sensation. Glare, reflections, dry indoor air, contact lenses, and uncorrected vision can worsen these symptoms. Temporary discomfort is not the same as permanent eye damage, and the distinction matters when giving advice. Looking into the distance, adjusting text size, reducing glare, and remembering to blink can support comfort. Let us return to the relationship between content and sleep. Emotionally intense material, social conflict, frightening news, or competitive games may increase mental arousal before bed. Arousal means that the mind and body remain activated when the person is trying to settle. Light and arousal can occur together, but they are separate mechanisms. A dim display does not make upsetting content emotionally neutral, while a bright screen can affect timing even when the content is calm. Practical responses should therefore address both technology and behavior. Turning off unnecessary alerts reduces external prompts to check a device. Charging a phone outside the bedroom reduces immediate access to it during the night. Silent mode removes sound, but the phone remains easy to reach if it is beside the bed. An ordinary alarm clock may replace the reason some users give for keeping a phone close. During study, placing the device out of reach, or using a focused mode, can protect periods of uninterrupted work. The aim is not to remove every digital tool, but to match access to the purpose of the task. Household approaches are more effective when expectations are clear and practical. Shared boundaries may specify screen-free meals, a stopping time before bed, or locations where devices are not used. Boundaries differ from vague instructions such as use your phone less, because everyone knows what behavior is expected. Adults should also consider whether their own behavior supports the rule they expect younger family members to follow. Strict limits without discussion may fail when schoolwork, transport, or social contact genuinely requires a device. Flexible rules can still be consistent if the reasons for exceptions are understood. Finally, researchers often discuss displacement. Displacement occurs when time spent on one activity replaces another activity that may support health or development. Screen use might replace sleep, outdoor movement, face-to-face conversation, or focused study. Yet it can also replace a less beneficial activity, or provide education and social support that would otherwise be unavailable. This is why duration alone gives an incomplete picture. Researchers need to know what activity occurred, when it happened, what it replaced, and how the person responded. To conclude, screen effects arise through several pathways rather than one universal mechanism. Light timing, delayed bedtime, notifications, task switching, inactivity, equipment position, visual demands, emotional content, and displacement can all contribute. Effective decisions depend on the purpose and context of use, not simply whether a screen was present.
Today's lecture examines research into food waste, including how waste is defined, how it is measured, why it occurs, and which responses are most effective. Food passes through farms, storage facilities, processors, transport networks, shops, restaurants, and homes before it is eaten or discarded. Waste can occur at every stage, but its causes differ across the system. Researchers often distinguish food loss from food waste. Food loss usually refers to reductions during production, harvesting, storage, processing, or transport before products reach the retail stage. Examples include crops damaged during harvesting, milk spoiled without refrigeration, and fruit rejected after rough transport. Food waste is more often used for edible material discarded by shops, food services, and consumers. The distinction is useful, although international studies do not always apply the terms in exactly the same way. Comparisons are therefore meaningful only when researchers state which stages and materials they include. Should inedible bones, shells, and fruit stones count, or only material that could normally have been consumed? Does a crop left in a field count if there was no buyer, and how should animal feed be classified? These boundary decisions can change the reported total substantially. We can now consider measurement methods. The simplest method is a questionnaire asking households how much food they discard and why. Questionnaires can reach many people cheaply, but respondents may forget small amounts or give answers they consider socially acceptable. A food diary records discarded items closer to the time when disposal occurs. Participants note the type, amount, reason, and disposal route for each item over several days. Diaries provide detailed context, yet they require effort and may still underestimate waste. Participants sometimes change their behavior because they know it is being monitored. This response to observation means the study itself can reduce the activity being measured. A second approach is a physical waste audit. Researchers collect or sample rubbish and sort the discarded material into categories such as vegetables, bakery products, meat, and prepared meals. Each category can then be weighed, photographed, or assessed for whether the food was avoidable. Audits measure what was actually placed in bins, but they are labor-intensive and raise hygiene and privacy concerns. They also miss material poured into sinks or disposed of through waste grinders. To investigate that route, researchers may use wastewater analysis and estimates based on substances found in sewage systems. This method can improve the total estimate but may not identify the exact product or reason for disposal. Municipal collection records provide another source of data, although mixed rubbish makes food difficult to separate unless a dedicated collection service exists. No single method captures everything, so strong studies often combine diaries, audits, interviews, and administrative records. Let us turn from measurement to causes. Date labels are a frequent source of confusion. A use-by date is generally placed on highly perishable food and concerns safety after the stated date. By contrast, a best-before date usually concerns quality, meaning flavor, texture, or appearance may gradually decline while the product may remain safe if stored correctly. Consumers who treat both labels as identical may discard food unnecessarily. Clear wording helps, but labels alone cannot compensate for poor refrigeration or damaged packaging. Retail promotions create another possible cause. A multi-buy offer can reduce the price per item, yet it may encourage shoppers to purchase larger quantities than they can consume. The saving disappears if the additional food is thrown away. Promotions are not always harmful, however, because shelf-stable products can be stored and planned purchases may be used later. The effect depends on product life, household size, storage space, and whether the purchase was intended. Household organization is equally important. Poor meal planning can lead to duplicate purchases, ingredients without a clear use, or fresh food that remains in the refrigerator until it deteriorates. Checking existing supplies before shopping and planning several flexible meals can reduce this problem. A shopping list supports the plan, but it works only if the buyer follows it and adjusts for unexpected schedule changes. Storage knowledge also affects waste. Some produce lasts longer when refrigerated, while other items may lose flavor or texture at low temperatures. Freezing can extend useful life, but consumers need suitable containers, labels, and enough space to see what has been stored. Food hidden at the back of a crowded refrigerator is easily forgotten. Restaurants and institutional kitchens face different problems. Demand is uncertain, so kitchens may prepare extra meals to avoid running out. Some waste occurs during preparation, and further waste returns on customers' plates. Offering smaller portions can reduce plate waste while allowing customers to request more if needed. A smaller plate may also influence perception, but portion size is the amount of food actually served. Kitchens can record which dishes are repeatedly left and then revise recipes, serving sizes, or menus. A buffet requires particular attention because abundance is part of the display and food safety rules may prevent reuse after service. Responses to surplus food follow a hierarchy. Prevention is usually preferred because it avoids the land, water, energy, labor, and money used to produce food that is never eaten. Retailers can improve forecasting, relax purely cosmetic standards, discount products approaching their date, and redesign package sizes. If edible surplus remains, it may be redistributed to charitable organizations that can store and deliver it safely. Redistribution provides social benefits, but it does not remove the need to prevent persistent overproduction. Donated food must also be appropriate, traceable, and collected while it is still usable. Material unsuitable for people may sometimes become animal feed, subject to health regulations. The remaining unavoidable material can be treated biologically. Composting uses oxygen and produces a material that can improve soil. Anaerobic digestion occurs without oxygen and produces biogas as well as a nutrient-rich residue. The gas can supply heat or electricity, so digestion recovers some energy from material that can no longer be eaten. Both systems require clean separation because plastic, glass, and other contaminants reduce product quality and damage equipment. Sending food to landfill is generally less desirable. In oxygen-poor landfill conditions, decomposing food can release methane, a powerful greenhouse gas. Gas collection reduces some emissions but rarely captures every release, and the nutrients in the food are not returned efficiently to productive soil. Researchers evaluating an intervention must look beyond the weight of waste alone. A small amount of wasted meat may represent more land and emissions than a larger weight of some vegetables. Packaging can prevent spoilage but creates its own material impact, so removing packaging is not automatically the best outcome. Studies should measure unintended changes, costs, participation, and whether the effect continues after a trial ends. To conclude, food waste is a system problem rather than one careless action. Reliable evidence requires clear definitions and several measurement methods. Effective policy follows the chain from prevention and redistribution to biological treatment, while matching each response to the stage where waste occurs.
Today's lecture examines ocean pollution, where it comes from, how it moves, what effects it produces, and how it can be controlled. The ocean is vast, but it is not isolated from activities on land, in the atmosphere, or at sea. Pollutants enter through rivers, drains, direct discharge, shipping, fishing, airborne deposition, and accidents. Once present, they may dissolve, attach to particles, sink into sediment, remain near the coast, or travel with currents. The outcome depends on chemical properties, weather, water movement, temperature, and the organisms exposed. Let us begin with land-based pollution. During rainfall, water flows across roads, fields, roofs, construction sites, and other surfaces. This surface runoff can carry soil, oil, litter, fertilizer, animal waste, and industrial residues into streams and rivers. A discharge from one pipe is called a point source because its location can be identified clearly. Runoff from a large area is described as diffuse pollution and is often harder to monitor and regulate. Urban drainage can deliver a concentrated pulse after a storm, especially when rain follows a long dry period. Agricultural land creates a different but equally important pathway. Fertilizers and animal manure add nutrients, particularly forms of nitrogen and phosphorus, to soil. Crops use part of this material, but rainfall can carry the remainder into groundwater, rivers, lakes, and coastal water. Nutrients are necessary for life, so their presence alone does not make water polluted. The problem occurs when supply exceeds the amount that the ecosystem can absorb without major change. Excess nutrients stimulate rapid growth of microscopic algae and other aquatic plants. These events are known as algal blooms, and some spread across very large areas. A bloom may block sunlight from reaching plants below the surface and can alter food web relationships. Certain species also produce toxins that harm fish, shellfish, marine mammals, birds, or people. However, not every bloom is toxic, and an intense non-toxic bloom can still create serious effects. When the algae die, bacteria break down the organic material. Bacterial decomposition consumes dissolved oxygen in the surrounding water. If oxygen falls below the needs of fish and bottom-living animals, they may move away, become stressed, or die. Extremely low oxygen regions are sometimes called dead zones, although some microbial life remains present. Warmer water generally holds less dissolved gas, so high temperature can make oxygen depletion more severe. We can now turn to plastic pollution. Plastic enters the sea through poorly managed rubbish, storm drains, rivers, coastal recreation, shipping, and fishing activity. Large items gradually fragment under sunlight, wave action, and physical abrasion. Fragmentation makes pieces smaller but does not mean the material has disappeared chemically. Microplastics are commonly defined as particles smaller than 5 mm, although research methods differ in the smallest sizes they can detect. Some microplastics are manufactured at a small size, while others form through the breakdown of larger products. Marine animals may mistake plastic for prey or consume it while filtering water and sediment. Plastic ingestion can occupy space in the digestive system, damage tissue, or reduce feeding, although effects vary with particle size and species. Finding plastic inside an animal does not by itself prove severe harm. Researchers must compare dose, condition, growth, and survival. Plastic surfaces can also carry organisms and chemicals, but their importance relative to other exposure routes remains under investigation. Fishing equipment creates a distinct physical hazard. Nets, lines, ropes, and traps may be lost during storms, abandoned after damage, or deliberately discarded. Animals can be injured or killed through entanglement when material restricts movement, feeding, breathing, or growth. Lost gear may continue catching fish and other animals for months or years, a process often called ghost fishing. Marking equipment, providing disposal facilities, reporting losses, and retrieving high-risk gear can reduce the problem. Chemical pollution includes a wide range of substances rather than one single category. Metals occur naturally, but mining, industry, fuel use, and waste disposal can increase their concentration in marine environments. Oil can enter through major spills, yet smaller routine releases and land runoff also contribute over time. Some manufactured industrial compounds are persistent because they resist physical, chemical, and biological breakdown. Persistence allows them to remain in water, sediment, or organisms long after their release. A persistent substance is not automatically the most toxic, but long residence time increases opportunities for exposure and transport. Scientists also examine how chemical concentration changes in living organisms. Bioaccumulation occurs when an organism takes in a substance faster than it can remove or break it down. Concentration may therefore rise in its tissues during repeated exposure over time. Biomagnification is related but different. It describes increasing concentration at higher levels of a food chain when predators consume many contaminated prey. A chemical can bioaccumulate without strongly biomagnifying, so the two terms should not be treated as interchangeable. Pollution is not limited to physical materials and chemicals. Ships, construction, sonar, seismic surveys, and offshore machinery introduce sound into the marine environment. Many marine animals use sound to communicate, find partners, locate prey, navigate, and avoid danger. Underwater noise can mask biologically important sounds when frequencies overlap and reduce the distance over which a signal can be detected. Loud or sudden sound may also cause stress, displacement, temporary hearing effects, or physical injury at close range. Responses differ among species because hearing ranges, behavior, depth, and previous exposure vary. Reducing ship speed, changing routes, scheduling construction, and improving machinery design can lower some acoustic impacts. How should ocean pollution be addressed? Beach and river cleanups remove visible material and provide useful information about common items. They also engage communities, but they recover only a fraction of pollution and cannot easily remove tiny particles or dissolved chemicals. Treatment systems can capture sewage, industrial waste, and some storm water before discharge. Better agricultural timing, soil cover, buffer vegetation, and accurate fertilizer application can reduce nutrient losses. Product redesign, reuse systems, fishing gear management, and producer responsibility can address waste further upstream. The most effective long-term strategy is pollution prevention, stopping harmful material before it reaches rivers and seas. Prevention is usually less expensive and more reliable than attempting recovery after pollution has dispersed. Monitoring remains necessary to identify sources, test whether controls work, and detect unexpected changes. Researchers must use consistent sampling because tides, seasons, storms, depth, and location can produce large differences. To conclude, ocean pollution involves multiple sources and pathways with interacting biological and physical effects. Effective management combines source control, treatment, monitoring, enforcement, and international cooperation. Understanding the chain from release to exposure to effect allows limited resources to target the most important causes.
Today's lecture examines memory and learning, with particular focus on how information is processed and how study methods influence later performance. Memory is not a single container in which experiences are placed unchanged. It involves several processes that select, transform, maintain, reorganize, and later reconstruct information. Learning can be demonstrated through improved knowledge or skill, but immediate performance does not always predict what will remain after a delay. We will begin with the formation of a memory. The initial transformation of incoming information into a representation that the nervous system can use is called encoding. Encoding can emphasize sound, appearance, meaning, location, movement, or connections with previous knowledge. The form of processing affects which cues may later help a person remember. Simply placing information in front of a learner does not guarantee that useful encoding occurs. One reason is that the environment contains more input than can be processed deeply at one time. Selective attention determines which information receives priority and which remains only weakly processed. A student may look directly at a page while mental resources are directed toward a conversation or an unrelated concern. The visual material reached the eyes, but it may not have received enough processing to support later recall. Divided attention is especially damaging when both activities require conscious decisions or verbal processing. Familiar background activity may cause less interference, but its effect still depends on task difficulty and the individual. Information that receives attention often enters a limited active system. Working memory temporarily holds and manipulates a small amount of information needed for the current task. It allows a reader to connect the beginning of a sentence with its end or to retain numbers while performing a calculation. Capacity is limited, so too many new elements can overload the system. Grouping separate elements into meaningful units, often called chunks, can reduce the apparent load. Expertise helps because familiar patterns can be treated as one organized unit rather than many unrelated details. However, a chunk is useful only when the learner already understands the relationship among its parts. How can active information be maintained and connected with longer-lasting knowledge? One approach is simple repetition, such as saying a phone number again and again. This is called maintenance rehearsal and can keep material available briefly. Maintenance rehearsal is less effective for durable understanding when the learner does not consider meaning or relationships. Elaborative processing asks how a new idea relates to an example, cause, category, image, or existing concept. Explaining an idea in one's own words can reveal whether understanding is genuine or whether familiar wording merely creates confidence. Organization also supports learning. A structured outline, comparison table, or concept map can make relationships visible, but the learner must decide why items belong together. Copying a completed diagram without thinking may produce an attractive page with little learning. We can now examine what happens when information is needed later. Retrieval practice means attempting to bring information to mind without first looking at the answer or notes. Examples include answering a question, explaining a concept from memory, or completing a blank diagram. The attempt itself strengthens access routes and shows the learner what is not yet available. An unsuccessful attempt can still be useful if the correct answer is checked soon afterward. By contrast, repeated rereading often creates familiarity because the page becomes easy to recognize. Familiarity can be mistaken for mastery, although recognition with the text present is easier than producing an answer independently. Practice should therefore resemble the kind of use expected later. If an examination requires explanation, studying only through multiple-choice recognition may provide incomplete preparation. Timing also matters. The spacing effect refers to improved long-term retention when learning sessions are distributed over time rather than concentrated in one period. A single long session may produce strong performance at its end because the material is still active and familiar. After a delay, however, some forgetting makes the next attempt more difficult and requires genuine reconstruction. That effort can strengthen later retention, provided the task is not so difficult that the learner cannot recover the information at all. The best interval depends on how long the material must be remembered and how complex it is. Spacing does not mean studying rarely, it means returning at planned intervals before knowledge is completely lost. A related strategy concerns the order of practice. Interleaving means mixing related categories, topics, or problem types rather than completing one entire type before moving to the next. Blocked practice feels easier because the learner already knows which method should be used for every item in the block. Mixed practice requires the learner to identify the type of problem and select an appropriate method. This can reduce performance during practice but improve later discrimination and flexible use. Interleaving is most helpful when the categories are related enough to be confused and when comparison reveals important differences. Randomly combining unrelated material does not automatically create a learning benefit. Learning continues after a study session ends. Memory consolidation refers to processes that stabilize and reorganize a newly formed memory over time. Sufficient sleep supports consolidation and also restores the attentional control needed for learning the following day. Different features of sleep may contribute to different forms of learning, and the effects are not limited to one single stage. Reducing sleep to gain extra study time can therefore be counterproductive, especially across several nights. Quiet rest after learning may also reduce interference, but it does not replace an adequate sleep schedule. Effective practice requires information about errors. Corrective feedback helps learners identify what was wrong, understand why, and choose a better response next time. A score alone indicates the amount of success but may not explain how performance can improve. Feedback is most useful when it is specific, understandable, and close enough to the attempt for the learner to connect the two. Immediate correction is valuable for a misconception that might otherwise be repeated. A short delay can sometimes encourage reflection, but a long unexplained delay may weaken the connection with the task. Learners also need another opportunity to apply the correction rather than merely read it. Finally, education aims for more than success on identical practice items. Transfer occurs when knowledge or skill is applied successfully in a new situation. Near transfer involves a context similar to practice, while far transfer requires use across a greater difference. Transfer is not automatic simply because a general principle was mentioned. Learners need varied examples, explicit comparison, and practice deciding when a principle is relevant. Too much variation at the beginning can overwhelm a novice, so support should decrease as understanding develops. Teachers can first demonstrate a method, then provide guided examples, and finally ask learners to choose and justify a method independently. To conclude, effective learning combines accurate initial processing with repeated opportunities to reconstruct and apply knowledge. Attention and working memory support the first stage, while elaboration, retrieval, spacing, interleaving, sleep, and feedback strengthen later use. The best strategy is not always the one that feels easiest during practice. Desirable difficulty can produce more durable and transferable learning.